permitting. Afterwards, on site, we do have viewing using our telescopes because unfortunately we're still under COVID restrictions. Our club-owned scopes are currently set up so for electronically assisted astronomy, where we have, instead of an eyepiece, where we have the eyepiece normally, we have a camera attached, and that inputs to a computer, which then projects the image that you would see through the scope onto a screen. So, part of our program is, since we started doing this about halfway through our season last year, when we got the go from the board, we started doing this online. So all of our programs are actually streamed live every Saturday that we have them, and you can find them on YouTube. You can also find all our past presentations since we've started doing this on our YouTube. So if you happen to miss us live or can't make it, you can always check out the past presentation. So, well, it looks like maybe they parked a couple cars. So while I'm waiting to see if anyone is wandering down, I am monitoring the online chat for this. A couple notes for you guys in the audience here. If you need to use the bathroom, we have the porta potty to my right or your left. After the presentation, I will be manning the little gift shop to my left through this door, the smaller door, not these double doors that I'm standing in front of. And since we are a nonprofit, all proceeds of that do go to keeping our lights on. Any donation keep helping upkeep with our maintenance of telescopes and whatnot, and also helps with offering our free public outreach, because these programs are completely free, and we hope to get them out to as many people as possible. And with that note, do check us out. Our website is uacnj.org. You could find information on our organization, our member clubs, our various telescopes that we have, as well as various science projects we got going on from the colleges that we have partnered with. So, let's see. Another thing to note, if we have lights, please point them down towards the ground. It's painful to get lights in your eyes. However, when you are leaving in your car, please do use your headlights. No one likes getting run over. And we like to keep our record this year of 0 people hit. I got hit once. It wasn't fun. That's what I get for not wearing my safety vest. So, in addition to our website, you can also check us out through our Facebook, Instagram, Twitter. We also now have a Discord server. If any of you, the younger people, I'm sure, who are into gaming know what that is. And also, like I said, we are a nonprofit, so you can make donations through our PayPal. Information is on our website. Also, we now have a Patreon. So if you're looking for a small way to support, that is a monthly recurring subscription. So with that, let's get started into our presentation. Tonight's presentation is The Beauty and Power of the Universe with Walt Windish. Walt has been interested in astronomy since he saw the Pleiades as... Yes, that is the Pleiades. I read that correct. As a Boy Scout, he bought his first telescope in 1985, just in time to see Halley's Comet. Walt is a member of North Jersey Astronomical Group and the Rockland Astronomy Club. He's been volunteering at Jenny Jump for over 20 years and using photos from the Hubble Space Telescope and ground-based images will explore stunningly beautiful objects in the universe and discover the enormous power that lies behind them. And with that, here's Walt.
All right, thank you. Good evening. Thanks for coming.
Thank you.
How many are sleeping down the bottom of the mountain tonight? Anyone? Oh, no one. Wow. What a perfect weekend for that. Oh well. Little trivia on the Pleiades, since we mentioned that. Anyone know what the Japanese name for Pleiades is? It's Subaru. That's why you got the stars on front of the Subaru emblem. And it's the Seven Sisters, but the Subaru emblem only has 6 because the 7th sister is blind. So I guess they decided to keep her off. That's being very ableist. But yeah, so Subaru is Pleiades. And what I'd like to do tonight is just go through some of the objects that I think are really beautiful out there. We'll talk a little bit about the science behind them, but I also want to talk about the power behind them as well. You know, we see them out there, these beautiful pictures, and a lot of times we don't think of the unimaginable power that's behind those things. You know, we look at science fiction and, you know, the Death Star and this kind of stuff, but this is real stuff. It's more exciting than science fiction. I love science fiction. I find it more exciting than science fiction because it's really out there. And the power behind some of these objects is just unimaginable. So let's take a look. I'm also going to take you time traveling. Does anybody have any idea how I can take you time traveling?
Further out you look, earlier the time period.
Exactly. Thank you. The telescope is really a time machine. And the further out we look, the further back in time we look. For example, this little square here is enlarged, and we see a little blip. It's not very impressive blip, but that little blip is galaxy MAX 6047. Scientists estimate that it's about 13.3 billion light years from Earth. So what does that mean? That means the light from this distant galaxy took 13.3 billion years to reach us so we could take a photograph of it. That's only 420 million years after the Big Bang happened. So the light from this galaxy has been traveling towards us for most of the entire history of the universe. And it left that galaxy before this solar system even formed, which is about 5 billion years ago. And this is 13 billion years ago. So the telescope's going to be our time machine. It's going to give us glimpses of how certain objects look at different points in time. Difference between this time machine and our history is we know what happened today, and we can look backwards in time as far as we possibly can, or know the history. But in the time machine of the telescope, we don't know what happened more currently until that light reaches us. So we're not going to know what happened to that galaxy today for another 13 billion years or so. So it takes a lot of patience to keep up on current events in astronomy. You know, the light from the sun is 8 minutes old. So when we see something on the sun, we're seeing an 8-minute-old image. The moon is about 239,000. So the light from that moon is only a second old. That's pretty good. If something happens, we'll know about it real quick. Of course, light travels at about 186,000 miles per hour, but sound only travels at 186,000 miles per second. That's why it seems instantaneous. But sound only travels at 1,100 feet per second. And so if something happened on the moon that we could actually hear, it would take about 14 days before we could hear it, because that's how slow sound travels next to light. One practical application of this is when you're in a thunderstorm and you see lightning. If you start counting 1, 1,000, 2, 1,000, 3, 1,000, every 5 seconds is 1 mile. So when you see the lightning, if you count 5 seconds, that means the storm's a mile away. And if you keep counting, you can tell whether the storm is moving closer or further and just how close it's going to be. When it's instantaneous, I don't have to tell you, it's right over your head. One more science concept I just want to talk about, and that's the electromagnetic spectrum. That's a really bright slide, isn't it? Whoa. It's the brightest in my bunch. So the electromagnetic spectrum covers everything from radio waves to gamma waves. And our eyes can only see this little rainbow area. A very thin slice of the electromagnetic spectrum can be seen by our eyes. But the instruments that astronomers use can detect that entire spectrum. And so we can get information that our eyes and even cameras can't. Cameras can get the information by using special instrumentation that's sensitive to that. So not only do we get beautiful pictures, but we can look to the left at real high energy objects, and we can get some pictures of that as well. Back to low. So the galaxy we saw is really, really old, but there's one that's older. And I just read about it this December 2020. And that's this galaxy right here. It's got the name GN-Z11, but it's now thought to be the farthest and the oldest galaxy ever observed. And it's superimposed on the image. You could see that little crosshair. That's that little tiny crosshair that seems to have nothing there. That's where they saw that galaxy. And it seems to be about 13.4 billion light years, so another 100 million years older. Not sure how accurate that is. I mean, the other one could be older. I'm not sure, but scientists are pretty sure this is about 100 million years older. It's 13.4 billion light years is 134 nonillion kilometers. So that's 134 with 30 zeros after it. That's how many kilometers away it is. Let's just say it's far away. And the Hubble telescope, the instrumentation on the Hubble telescope is kind of interesting. Didn't have as good a resolution as they needed to get this picture, but they had more advanced instrumentation at the Keck telescope in Hawaii, and that was able to bring in a picture that was used to derive this photo. So the Hubble telescope has the advantage of being above all this atmosphere, but the Keck telescope has more advanced instruments, and even 10 years makes a big difference in instrumentation, and so it gave us better pictures. You know, when you think that the difference between the Wright brothers taking up a kitty hawk and us landing on the moon is less than 70 years. That's an amazing amount of technology that happened between those two events. And the technology to make our instrumentation is just amazing. So here's an example of using infrared light to detect an obscure object. These are called Herbig-Haro objects. It's really a protostar that's throwing off jets of energy, but it's so covered up in dust, a camera can't see it. You can't see it with any telescope unless it's looking at the infrared spectrum. This photo was taken in visible light. It was taken by the Hubble, and this is a real dramatic example, I think, of what different wavelengths can produce as far as a picture. So this is called the Eagle Nebula, and it's basically a star factory. When stars are born, big clouds of dust get closer and closer together. The gravity pulls them together, and when they get close enough and hot enough, they ignite into a protostar. And so a lot of stars are being born all through here. It's about 6,500 light years away. Some estimates go as high as 7. So we're looking at the object as it appeared 6,500 light years. And just to give you a scale, from here to here is 4 light years. So it takes light 4 years just to travel the length of this pillar. The scale is just amazing. So let's look at the same field of view through the same telescope, Hubble, but using an infrared camera. And what do we see? Quite a different picture. See, the infrared really cuts through dust and reads the heat. And so we can get a lot of more information about the stars that are being born here, some of which were so obscured by dust we couldn't even tell they were there. And that's how we use different types of instruments, even with the same telescope, to get very different photos. That's a side-by-side comparison to show you the different information. So you can't even see this quad right here. Maybe just a hint of it. So now let's take a look at a wide view area of the same nebula, the Eagle Nebula. Here it is. Do you see the pillars? The pillars of creation, or the Eagle Nebula, is right here. There they are. So when you look at that, that's 4 light years. So we're looking at a huge 70 by 55 light year view of this area. And there's a really hot star cluster here, NGC 6611, right here. And you could see that in a backyard telescope, 6 or 8 inch backyard telescope. It's not a difficult object. But these are hot young stars, and not only are they illuminating. Think of what it takes to illuminate these pillars from up above, like three light years away. I mean, you think the sun's bright. The closest star to us is 4 light years away. Could you imagine if there was a star there that threw so much light that we'd have this much light thrown upon us? It's just amazing. It also, the winds from this evaporate the clouds in a process called photoevaporation. It's kind of like if you were looking out west at the Hoodoos, where there's tall columns of rock. Well, those columns of rock didn't grow like that. Erosion wore out in between. The weaker sections of rock got wore away, and the taller ones were left. Well, it's the same thing here. The wind from this star cluster is blowing this gas away, and it's left the strongest, most dense gas behind, which is the perfect birthplace for stars. So we got a lot of ultraviolet light illuminating that. You get a heck of a suntan. Interesting thing now, earlier images from the European Space Agency and the XMM Newton and such have led scientists to believe that one of these stars here went supernova 6,000 years ago. So if that's true, if a star here went supernova, this whole area is all blown away by a shock wave. There would have been a shock wave that would have just taken all of this out. But again, this is 6,500 light years away. We're going to have to wait 500 years to see if the astronomers, the astrophysicists, were correct about that. So stay tuned. We'll find out. So I started on this journey with the Eagle Nebula because I thought it was a perfect combination of beauty, power, and time travel, and the importance of what we can know by looking at light that's as old as some of these objects are. We can make predictions, and it takes 500 years to find out if they're right or not. You have to be very patient in astrophysics. It was, one of the quicker confirmations was Einstein's theory of relativity. That only took us less than half a century to confirm, but it took quite a while to confirm. And some of the effects Einstein himself didn't even like. He didn't like the idea that the universe was not eternal, that it was expanding, and so if we pull it back together, there must be some kind of beginning to it. At first, Einstein found that he even made the biggest blunder of his life by making a correction so that the universe would be a steady state instead of expanding. But we know for sure that it's not only expanding, but we think it's expanding at a faster and faster rate, which is incredible. Okay, so before we get too far out in space, let's reel it back in a little bit to our solar system. Anyone know what type of object this is? Comet. Excellent. Yeah, comets are usually part of our solar system. Up to a couple of years ago, I would have said they're part of our solar system, but we've seen a couple of comets that have come outside of our solar system on a parabolic orbit, where it comes into our solar system, goes around the sun, and then goes out. Most comets have an elliptical orbit with the sun at one foci, and they just go around and around, different periods. This comet, Comet Hale-Bopp, which was discovered in 1995, has a period of about 25,000 years, 2,500. So that means we won't see this again for another 2,500 years. Its nucleus is about 25 miles across. And you can see it's got two tails. The beautiful thing about this comet is the two tails are so distinct. This is an ion tail, and the ion tail is light gases, and so it always points directly away from the sun because the solar winds affect the tail the most, and so the solar winds will blow this in the exact opposite direction of the sun. This is the dust tail. The dust tail has heavier particles, and so it's more affected by the motion of the comet, and so it lags where the comet goes. So just by looking at this picture of the comet, we can tell that the sun is down here and the comet's moving in this direction because the tail is off to this side, and the heavier particles take a while to catch up to the ion tail. So you can get a lot out of that. This picture is one that I took. I took it right here on April 5th, 1997. And I used some cheap equipment that I put together. I'll show it to you in a minute. But that's a 4-minute exposure. It's a scan of a photograph. I really gotta scan the negative and do some Photoshop so it'll look more spectacular than that. But that was a really cool time. That's a 4-minute exposure. I took this one. That's about a 45-second exposure, and the camera was just on a tripod for this one. Opened the shutter for 45 seconds. If I opened it much more, the star field would have gotten blurred. And I used the real El Cheapo. That's what I used. That was taken. I was exhibiting that at a telescope makers convention. But it's just two pieces of plywood, a carriage bolt, a hinge, and a platform for my camera. I put a much better platform on. I spent about $100 on the platform for the ball joint for my camera. This is maybe $10 in parts, and there's a little crank here, and you do the math to make this board the right size, and if you turn the crank every minute, it keeps up with the rotation of the Earth. So I was there with a time station radio, and every 15 seconds I turned the crank a quarter of a turn, and I did that for 4 minutes and came out with that first picture that you saw. So you don't need to spend a whole lot of money, and I just used at the time it was a film camera. I just used a 50mm lens on a camera to take that picture. So I didn't spend thousands of dollars. I did later, but that's the disease. But comets are gorgeous. But there is a power side to the comet, and this is a couple of years earlier. This is comet. Well, this is. Does anyone know what that big round object is? Jupiter, yeah, Jupiter, and that's right up in the sky there. So yeah, that's Jupiter. And back in 1993, comet Schumacher-Levy was discovered. It was discovered about almost a year after its closest path to Jupiter, and the gravitational tidal force of Jupiter broke that comet apart. And so that happened in 1992, July of 92. In March of 93, the comet slammed into Jupiter. All the fragments slammed into it. There were 21 fragments, and they all hit on July 19th of 1994. They hit at a speed of 36 miles per second, causing plumes of smoke thousands of miles high. The largest of the fragments was 2 kilometers, so that's about 1.2 miles wide. That was the largest fragment. These plumes on Jupiter, these are the size of Earth. So you got 1.2 mile fragment makes an impact in a very gaseous gas giant about the size of the Earth. It's a lot of power there. This is a composite photo taken of all the incoming fragments coming into Jupiter. Okay, we're going to switch gears a little and talk about the life of a star. This is called an Hertzsprung-Russell diagram. And it plots how bright an object is against the surface temperature. And it found that there is a definite correlation between the two. And we use that to classify stars. So, this is the temperature scale. And this is the brightness. So, it goes to common sense. At any given temperature, the bigger the object is, the brighter it's going to be. So, the brightest objects are the biggest objects here. But we found that most stars fall into what we call the main sequence, which is right here. So once the star reaches equilibrium, it spends most of its life on the main sequence. And it shares, stars that are grouped together share similar characteristics, just like a periodic table of elements. But the difference is that the stars move through this diagram. They don't just stay in one place. They stay in one place for a long time. Like here's our sun right here. It's very ordinary. It's halfway in the luminosity, about halfway in the temperature. And it's going to sit there. It's been there for about 5 billion years. It'll be there for about 4 or 5 billion more. But then as it runs out of hydrogen to burn, it's going to start to change. And the characteristics are going to start to change. And we're going to see that it's going to move up here. And then it's going to finally end up down here as a white dwarf. And I'll show you that in a few minutes. But that's kind of the life of the star. Larger stars, about 8 times the size of our sun and bigger, they burn different types of fuel. They don't stop at carbon like our sun does. They would go all the way to iron. And when they hit iron, there's a catastrophic collapse, and you'll get most of the times, you'll get a type 2 supernova explosion, and you'll have something left behind. And we're going to take a look at the remnants. That's why I was going through this. We're going to take a look at the remnants of a star like our sun, and the remnants of a larger star as well. They can be quite beautiful. This is just an illustration how, as I said, our sun sits there on the main sequence. When it runs out of hydrogen, it starts burning some helium. It becomes a subgiant and then a red giant. When our sun becomes a red giant, the outside of the sun will reach to somewhere between Mars and Jupiter probably. So we'll be inside the sun at that point. Bring your suntan lotion. It then collapses. Most of the star, about half of the mass, collapses into a white dwarf, which is not burning anything, but it takes billions of years to cool down. But the other half becomes a planetary nebula, and it's just a gas circle, and we're going to see a whole bunch of different planetary nebulas next. The planetary nebula lasts for about 20 or 30,000 years, and it dissipates, and what's left is a white dwarf that spends billions of years cooling down. So here's a picture-perfect planetary nebula. And the reason they call them planetary nebulas is when they're originally looking through at with a telescope, they're little white fuzzy blobs. They look like little clouds, and they're round like a planet, and so they call them planetary nebulas. But they have nothing to do with a planet. It's a shell. It's the outside shell of a dead star. So this is the M57, the Ring Nebula, and here is here's the white dwarf. That's about a magnitude 13. It's a very, very dim star, but this is the star that blew off this big shell. It's called M57. It's a great summertime object. It looks like a smoke ring in the sky. Very cool. It's right in the constellation Lyra, and it's just about above our head. Again, the outside shell is only going to last for about 30,000 years. Now, if we take an infrared camera and we look at this object, this is what we get. There's what we were looking at, but look at this. You can see the outer shell of the red giant that was blown off. And you know, you can almost see the shock waves coming off of that, but you can only see that remnant in the infrared. This is what we see in visible light right here. And there's that star right there. Here's another, this is called the Dumbbell Nebula in Vulpecula. It's about 1,200 light years away from us. It was first described by Charles Messier in 1764. Messier came up with a catalog of what we call Messier objects. And they're all fuzzy little blobs up there. We call them nebula. A lot of them are planetary nebula. And he really was cataloging annoyances. He was a comet hunter. And he didn't want to spend any time on an object that wasn't a comet. So he cataloged all of these Messier objects so that he knew where they were and wouldn't waste any time wondering if they were a comet or not. And now people make sport of trying to see all the Messier 101 Messier objects in one night. And you can only do that in 1 or 2 nights in March, because some of them are below the equator, some are above. And so you'd need just the right season to catch them. This is a really cool one. That's called the spirograph, Hubble spirograph. This image is from year 2000, and its official and boring name is IC418. It glows like a multifaceted jewel. It's just amazing with very intricate patterns. You can see how it was named a spirograph. It's about 2,000 light years away from us. And this picture has been enhanced. A lot of pictures are enhanced to show different wavelengths. As I said before, we don't just use visible light when we take pictures of this. We use infrared, ultraviolet. We use all kinds of the electromagnetic spectrum. And so sometimes scientists will color code that to indicate what wavelength or what elements you're looking at. Here the red shows the emission from ionized nitrogen, and green is showing us hydrogen, and blue traces the emission of ionized oxygen. So we can tell what elements are in this picture as well, because of the color coding that the astronomers did. Here's one of my favorites. This is bizarre. This is called the Cat's Eye Nebula, NGC 6543. And again, it's another NASA Space Telescope image. What's really cool about this is there are 11 or more concentric circles. Do you see that? And each one of those is really a bubble around the central star. And it's like if we cut an onion and then looked at the profile of the onion, we would see the same thing. But each of these would encircle the entire thing. So we're looking at like an onion cut down there. And so scientists have all kinds of theories. Thankfully, none have anything to do with aliens. But it looks like those concentric circles were made at 1,500 intervals. And it's a real stumper. There have been theories about maybe there's a magnetic field, maybe there's an unseen companion star that is responsible for that. All kinds of good stuff. But the bottom line is we just don't know what made those bullseye pattern around that planetary nebula. And it's a very unique one. This is a pretty planetary nebula, is known as the Little Ghost Nebula, because it's round and it's very faint. It was discovered by William Herschel, and he was using a telescope to explore the constellation Ophiuchus. The nebula's main ring that you can see is a structure about 1 light year across, and it glows from ionized oxygen, hydrogen, and nitrogen. It's about 2,000 light years away from us. Now I'm just going to depart, since I'm on a ghost nebula view and we're coming up to October almost. I'll give you a couple more ghostly images. There's one. Now that's an emission nebula. That wasn't caused by a dying star. That's on the other end of the spectrum. That's dust. That's dust that's floating in space, and it's lit up by stars that are nearby. That's why we call it an emission nebula. But I like that one. That's called the Ghost Nebula. It's in the constellation Cephus. It's about 1,500 light years away. And these photos here are from my Halloween collection. I did a Halloween night one time here. I like this one even better. Very ghostly kind of a picture. The nebula is considered a globule. It's 2 light years across. And again, it's lit by stars that are embedded in it. And here's a ghost nebula and goblins. Again, globules. It's a wider crop of the same reason that we find the ghost nebula. Now I'll go back to one more planetary nebula. It's a really cool one. It's a very unusual one. The Butterfly Nebula. This nebula is found in Scorpius, and it's known as a bipolar nebula. It doesn't have to take lithium, but you can see that it does have 2 poles and a very tight ring. You can see that tight ring of gas all around it. It looks absolutely beautiful, I think, but there's tremendous power behind this one. The spectrum of the center star shows it to be one of the hottest stars known. It's got a surface temperature of 450,000 degrees Fahrenheit. Our sun is just under 10,000 degrees. So this is more than 45 times hotter than our sun. It must have been a fairly big star. But again, since it's a planetary nebula, we know that its mass was still probably less than 8 suns, because anything bigger causes a supernova, and this was not a supernova explosion. So the central star can't be seen because it's hidden with that donut of dust that I pointed out to you. And it appears as a dark band. It's probably the cause of the bipolar shape. It's probably restricting the center and causing the gas to shoot out both sides. The wingspan of this butterfly covers about 3 light years. And the outflows that we see are roiling cauldrons that are heated to about 36,000 degrees. So, I mean, it's hard to even imagine this object. And add to that, it's racing across space at about, what is it, 600,000 miles an hour. So it's expanding. These 36,000 degree gases are expanding at 600,000 miles per hour. It's just mind-boggling to think that an object like that actually exists and looks so serenely beautiful when you look at it through a camera. That was taken on the wide field camera that was installed in the Hubble Space Telescope in 2009. So that was one of the last instruments that was placed on the Hubble. So we've taken a look at the dust cloud compressing, becoming a protostar, and becoming an average size star, just like our sun, 1 to 8 masses of our sun. The end, after it's done living on the main sequence, which in our sun's case, 10 billion years, we're about halfway through, it becomes a red giant when it runs out of hydrogen. And then finally, the shell becomes a planetary nebula, and about a half of the mass becomes a white dwarf. And the white dwarf spends billions of years cooling off as a very tiny star. So what happens if it's more the size of the sun? Well, if it's got mass 8 times or more of the sun, we take the bottom root. And depending on the mass, it'll become a red supergiant or an even larger supergiant, a super duper giant. Once it runs out of fuel to burn, they always stop at iron because iron needs more energy to burn it than it gives off. So stars will never burn the iron core. But once iron develops in the core, you get this shock where it collapses in itself and then it just explodes into the supernova. And one supernova can outshine an entire galaxy in brightness. They're just cataclysmic, amazingly powerful explosions. So we see the supernova, and then depending on its mass, it's either going to turn into a neutron star or a black hole. And we're going to take a look at both of those. So here's a Tarantula Nebula, and 1987A is one of the most studied supernovas in history. And here it is right there. You can see it's a camera just gets so overloaded you can't really tell the brightness, but this is outshining the entire galaxy. Some of the explosions, if they were close to here, we could see them during the daytime. And ancient astronomers, as I'll show you later, have seen some during the daytime. There's been none in modern history. No supernova's gone off close to snuff, but both Tycho Brahe and Johann Kepler observed naked eye supernovas during their lifetime. And in 1987, this went off pretty close to us, but not close enough so that we could see it in the daytime. It was about 163,000 light years away still. And this is a ground-based telescope image about 2 weeks after this supernova went off. This is an artist's illustration of what that cataclysmic star collapse and explosion would look like after it bounces off its own nucleus and sends out a shock wave. Just a huge explosion. It's called a Type 2 supernova. And I'm oversimplifying. If you were to go on the internet and do some research on supernova, you would see that there are more and more types of supernovas that we're discovering. And our current classification system that was created over 100 years ago isn't adequate enough. And so scientists are battling whether they should come up with a new, more accurate classification system for all the different flavors of supernova there are. So I'm giving you a very simplified version because I'd like you to be awake when I'm done talking. So up to about a mass of 40, we get a neutron star that's left behind. A neutron star can have a mass greater than our sun, but only be 12 miles across. So when that core collapses, we're talking about an area the size of Manhattan having as much mass as our sun, or half of our sun, right? Our sun weighs 333,000 times more than Earth. So imagine half of that, 160,000 tons of Earth packed into space the size of Manhattan. I mean, that you couldn't lift a teaspoon of that, even if you had a crane. We're talking about a very tiny star that's about 1 trillion times more dense than our sun. That's what a neutron star leaves behind. Here's one of my favorite remnants of a neutron star. And there is a pulsar in there. This is the Crab Nebula, or M1. And this is a beautiful mosaic from Hubble. And it's about 6 light years wide. And it's an expanding remnant from a supernova explosion. What's really cool about this is that Japanese and Chinese astronomers saw this thing go off in 1054, and they have recorded it in their records that they could see it during the day for, I think it was about a week or two. Now it's magnitude 8.4. You need a telescope to see it. But it's just so cool to think that 1,000 years ago, there were people on this planet who actually saw this thing go off. And now, when I look at it in a telescope, I can see how much that gas cloud has moved out from the supernova explosion. There is a star embedded in the system. The neutron star is like a lighthouse. It spins around and around. It actually spins at 30 times a second. So think about the island of Manhattan spinning at 30 times a second and giving out, it's like a lighthouse. So on both ends, there are beams of energy, and that's why we call them a pulsar, because 60 times a second, they're sending out signals that we can see. Very, very cool. This is just a close-up, and there's the actual pulsar itself. It can be seen in that picture. This is a very tough photograph that was taken with the help of the Hubble telescope. It's called the Black Widow pulsar. I include it just because it's a very strange object. It weighs as much as 2 suns, but it's only as wide as Washington, D.C. So it's very, very massive. And it's got a mate. And we know what the Black Widow does with the mate, right? It eats the mate. And so this is the mate is a star that's much larger, about 8 times the size of Jupiter. So you've got this highly dense Black Widow pulsar, which is about the size of Washington, D.C., feeding off a planet that probably was a star at one time. That's about 8 times the size of Jupiter, which is gigantic. They call it a brown dwarf, a lightweight brown dwarf is the companion. So the 2 stars orbit around each other every 94 minutes or so, and the Black Widow is constantly taking gas off of that, off of the Jupiter-sized or the larger planet. And this is an actual photo taken in X-ray, and it's like the technology to see this is like seeing a flea on the surface of Pluto. I have no idea how they swung that through using X-rays, but it really was a breakthrough in science when they were able to image that Black Widow. The pulsar's beam just strips layers and layers off of its companion star. I keep saying planet. It's a star. It's a brown dwarf. So technically it is a star, and it's a very small star. Brown dwarfs, if they didn't have a Black Widow next to it, they're thought to be able to live for trillions of years. But since the universe is only about 13.7 billion years old, we don't really know for sure. But as the pulsar strips off gas, it makes it spin faster and faster. And pretty soon it'll be dancing only by itself. This is called a nanosecond pulsar because it spins 600 times per second. I'm sorry, millisecond pulsar is what it's called. So 600 times a second this thing is spinning. 2 masses of the sun the size of Washington. It's just, as I said, it's just mind-boggling. Here's a couple of artists' renditions. This is what one artist thinks that the Black Widow looks like against its star companion. There's the jets, and there's the gas field that it's secreting. You know, it rips the gas off, and then this is such a high gravitational pull that all of the gas just falls into it over time. There's another picture just to show the shock wave that it causes. It's moving through space about 10 times faster than our solar system is. So it's just crazy. There's one more picture. I kind of like these artists' picture. They do a pretty neat job of showing what the shock wave. This picture is supposed to be a 1,000,000 times magnification of this picture. So how they figure that out, go figure. You got to be a good artist to figure that out. Okay, so finally, we're going to take the bottom route, and we're going to look at black hole. All right, so if it's over 80 masses of the sun, if the star that went supernova was bigger than 80 times the mass of our sun, chances are it's going to turn into a black hole after it's had its supernova explosion. We think, right? I mean, that's the current scientific thinking. And so, there's an artist's conception of a black hole. The gravity in a black hole is so dense, no light can even leave. So you don't ever really see a black hole. What you can see, theoretically, and actually we did finally in the last couple of years, you can see the accretion disk, right? This gas is gas that's falling into the black hole, and it gets hot and it glows. And so if you're going to see a black hole, your best bet is to see all of the gas or stars that it's eating up in its vicinity. So you can see the accretion disk. You'll never see the black hole itself. Here's an artist's rendition of a black hole. Another thing that a black hole does, and this was part of Einstein's theory that took a while to prove, but a black hole actually bends space-time. And when you look around the black hole, one of the things you can see is this stretching. And you can also see gravitational lenses, which I'm going to show you in a couple of minutes. But the gravity is so intense that it actually bends the fabric of space-time around it and distorts everything around it. Not a very impressive picture, but it actually is. That is taken with the Event Horizon Telescope, and that's the first picture that we think we have of a black hole. I mean, we see the effects of black holes, but and again, of the event horizon of a black hole. There was quite a team that took these pictures. It was taken over the course of a couple nights in April of 2017, and then it took a couple of years to write the software that actually brought this image out of the data. It was quite a feat. It took a lot longer to write the software than to actually capture the data on a camera. And this black hole lives there. It's galaxy M87. It's about 55 million light years from Earth. It's in the constellation of Virgo, which is a summer constellation that we can see. Unlike the Milky Way's stunning spirals, M87 is just kind of a blobby galaxy. It's called an elliptical galaxy. Not nearly as pretty as ours. Now, gravitational lensing by very massive objects, as I said, is something that was predicted by Einstein and discovered in nature finally in 1979. Here's a more recent example. Right, take a look at these elongated objects. It's a giant lensed galaxy. This view of the galaxy, which is we think the galaxy is about 10 billion light years away, has been warped into nearly 90-degree arc of light by the gravity of the galaxies here. So this is a supermassive group of galaxies, and behind it is this galaxy, and it has bent space-time so that we can see behind it and magnified, but very, very distorted. And that's called gravitational lensing. It was first predicted by Einstein, and now we have photographic proof in a number of ways. And some of these lensing situations are very interesting. This is my favorite. This is called an Einstein cross. To me, this is mind-blowing. So you have a large cluster of galaxies that act as a gravitational lens, and you see these 4 dots? These 4 dots are the same supernova. There's a star behind those galaxies that went supernova, and the light from those stars was bent by the fabric of space-time and came out in the same image, slightly different times. You can see there's slightly different stages of going supernova, and they make the Einstein cross. Wild example of gravitational lensing. I mean, to be able to catch that is a great stroke of luck, actually. Here's another one. I like this one. You got the two galaxies, and they bend some other galaxies into a little face there. It's called gravity's grin. Some people call it the Cheshire Cat galaxy group. Right? They're distant galaxies and just kind of give a whimsical appearance. They were caught by both the Chandra X-ray telescope and the Hubble telescope. Let me just see how we're doing on time. Oh, perfect. Okay. The Great Carina Nebula is a jewel of the southern sky. Like the Orion Nebula in our northern sky, this is another star factory. A lot of stars are born there. This photograph here spans about 300 light years, so the nebula is just huge. And it's about 7,500 light years from us. Eta Carina is a great star. If you want to Google something to look at, this is a star that has all kinds of theories behind it. It's about 8,000 light years from us. Structures up to 10 billion miles across, which is the size of our solar system, are visible in this photo, which is some of the most detailed work that we have at that distance. It's you can distinguish dust lanes in it, tiny condensations, even strange radial streaks. And Eta Carina is over 5 million times larger than our sun, the star that's right there, 5 million times the size of our sun. But Betelgeuse is 300 times larger than Eta Carina, so it's not the biggest guy in the block, but he's pretty big. And about 150 years ago, there was a very bright outburst from this star. It looked like a supernova, and the surprising thing was that the star lasted through it. So the star released as much energy as a supernova explosion, but it survived, and somehow the explosion produced two polar lobes that we see here. So there's a dust cloud, just like we saw in the Butterfly Nebula. There's a tight jacket of dust here that's causing these two lobes of energy to go bipolar. And those lobes are expanding at about 1.5 million miles per hour. So again, the power behind this beautiful object is real. To me, it's incomprehensible. To be moving at 1.5 million miles per hour. There's very little dusty debris right at the star, and so we can see this blue light of the star being let out. But there's enough dust on both sides of it that it constricts the flow of the energy to the lobes. Again, this is taken in a different wavelength. I like the detail in this one more. And then finally, I'll leave you with this ghostly face of ARP 2026-424, 704 million light years away. It's two galaxies that are merging, and these are all new blue stars that are being formed by the merger of these two galaxies. and they form the nose and the mouth as well. But the ring structure is only going to be around for about 100 million years. The blue stars, about 100 million years, and then these galaxies should be done merging in 1 billion or 2 years. Again, amazing power behind these objects and beauty. Any questions?
All right.
Sure.
Hold on.
Oh, I'm
So
sorry.
we're going to do a Q&A session now?
Sure.
All right.
You're gonna...
So thank you, Walt, for the talk. Yeah, sorry to cut you off there. I know you have a question. Now's the time that we normally do a Q&A session. I have been monitoring chat, which is why you saw me over in the corner kind of typing away occasionally on my computer, because, you know, online people also would like some interaction. That being said, how we do this is, for those of you who are here in person, I'm going to bring the microphone out to you so that when you ask your question, our online audience can hear, because chances are if you have that question, they might also have that question and just have been too afraid to ask. And so since you have a question right away, I'm going to start off with you, and then I will also then go back and forth with the questions.
Great.
So raise your hand who was the one cut off. Okay. Hold on.
Okay. With the Big Bang, it contained all matter, which then supposedly exploded, and it should have been so massive that not light nor matter could have been released from it. So how it seems like it's a conundrum. If it should have been the mother of all black holes.
It certainly seems that it should be. Yeah. It was what scientists call a singularity, and you know, as I said, we know that the universe is expanding, and the evidence is that it's expanding at a faster and faster rate. And if you play that backwards, you get to the point of a singularity. The closer you get to that singularity, the more speculative the theories become, because nobody really knows. There's now scientists that think that there are multiverses, a number of universes that are existing at the same time. That's way beyond my pay grade, though, as far as explaining to you. I'd probably get a really good grant if I could come up with a halfway plausible answer for you. But you're right. It's just.
The mother of all black holes.
Yeah.
You need to get out of it.
Just thinking about it gives you intellectual constipation. For me, anyway.
All right. Thank you for that question. So our next question comes from our online audience, and they ask, what is your favorite night sky object?
Wow. I love the Pleiades because that was the first thing that turned me on to astronomy when I was a Boy Scout, and I saw a Little Dipper. I also love the Crab Nebula because Chinese and Japanese astronomers saw it go supernova in the year 1054, and saw the light, saw that star in broad daylight. So those two, probably my favorites.
All right. And on that note, there was actually another person who had added to that question, and they suggested viewing the Sombrero Galaxy. They really liked that one.
That's a very cool galaxy. So. Absolutely. I should add that. I don't think I've included that in any of my talks. That's a great suggestion.
That would be one I would think we would have in May.
Mm-hmm.
For Cinco de Mayo. That would be a good one.
There you go.
All right. So hold on. Let me just walk out.
Isn't the Milky Way bound to collide with Andromeda?
Yes. Yes, they are moving.
Go ahead. Sorry. Okay.
No, you're correct. The two galaxies are moving just as we saw. These two galaxies moving together, and you see the Whirlpool Galaxy as well. You see two galaxies colliding. That's what will happen to the Andromeda. And you think it's cataclysmic, but there's so much space between the stars. It's not quite as cataclysmic as you would think. As I said, the closest star to here is 4 light years. There's a lot of space. Now we looked at the Eagle Nebula though, and we saw some star clusters that were, they were packed, and there's globular clusters as well that are packed with stars in a much smaller area. But it's not quite as cataclysmic as you would think. But there's a lot of energy. I mean, look at all these brand new stars being formed because there's a lot of dust that collapses and ignites into new stars. That's great.
All right. Sorry, I was trying to scroll to the question. I'm like, I knew there was another one here. The next question is, what is your favorite place to go view the sky?
To view the sky.
Stargazing.
Well, Jenny Jump is certainly one of my favorites. It's only an hour from home, and the skies are much darker than I live further east. So as far as New Jersey, this is great. I love the Adirondacks. I love Maine, has some great skies. Hawaii, yes, I have been to Maui and the Big Island. I've observed on and yeah, those are a little heavier on the pocketbook than driving the Jenny Jump, but absolutely stunning. And you're further south. You're down around 20 degrees northern latitude, so you can see some stuff below the equator that you just can't see here. So yeah, that's an amazing place to view.
All right. Was there another question from our audience? Oh, I see a hand. Hold on. Can you raise your hand again because I lost you? Thank you.
My question is, do we know how fast our sun is moving within our galaxy?
Yeah, I had I don't have that off. Let me think for a second. I had that. Where did I have that? Give me 1 minute. I'll see if I can come up with it quick. Do you know? Go right ahead. I'm looking at something.
Everybody.
Hold on, Ken. Let me get you.
This is wonderful.
Hold on.
So, without even
moving out of your chair. Oh, hello. Without moving out of your chair, well, actually, you might have to. Everybody, stand up if you can. This is the International Space Station flying over.
Oh, there we go.
That is the International Space Station flying over UACNJ.
Nice.
Everybody wave. Oh, I saw him wave back. I do believe that now it's disappearing because the shadow of Earth is now covered it, and therefore we can't see it anymore.
Thank you.
All right.
And while we're standing right behind us, that's Jupiter, and there's Saturn to the right. Those are 2 planets that we can see right from here. And we'll be getting some good telescope views of that.
All right. Thank you, Ken, for bringing that to our attention.
And any other questions? I didn't have that the sun speed for you. Sorry.
All right.
I'm not sure now. I have the kilometers per hour in my notes somewhere, but all right, well, have fun observing.
Hold on. Were there any last-minute questions? Oh, hold on.
How do you know the weight of these things? I've noticed that you mentioned different weights, and we don't have scales in space.
Yeah. That's, a lot of it is by the way that they affect other objects. And the way that they warp space-time. That's the best answer I could give you. They have many different tools, but it's mainly the gravitational effect on the objects around it and how they act. But yeah, and when you talk about the density of black holes, that's the fringe of science. But as far as the pulsars and the way that they affect the stars around them is a pretty well set. I can't even think of the word right now. Their effect on other is pretty well set in scientific knowledge and astrophysics.
Right. So
Yeah.
I have another question from actually online. Is there a chance of life out there in the universe, given the Fermi paradox? That's not one I'm actually familiar with.
No, right. Well, I mean, to answer the question, yes, there's certainly a chance of life out there. I don't doubt that there's a chance.
Right. So, well, I have put out a last call online for questions. I still have a good half of you here and maybe half of your attention. I just want to go over a couple things because I know a couple of you who are here in person came kind of halfway into the show and haven't been given the briefing. If you do need to use the restroom, the porta potty is to my right, your left. It's lit up by that lovely red light. We do have a gift shop. All the donations and sales do go to support keeping our lights on, maintenance on the telescopes and grounds, and help us keep offering the free public programs. Do check us out on our website, uacnj.org. It has all sorts of information on space, our member clubs, our instruments here. When you do go to leave, please use your headlights. We don't like getting run over, and I'm sure your insurance would appreciate you not running over other people. So, we do have a number of scopes open. Some are in the observatories. We do have personal scopes set up on the lawn. A couple things to note: please ask before you go touching a telescope. I do know there are a couple visitors who have brought their own telescopes, and you want to make sure that they are okay with you touching their telescope before you use it. Also, any of our United Astronomy Club telescopes will have cameras attached to them, so you can view the images through them on a screen. If there are telescopes that you can look through an eyepiece, they are not UAC&J telescopes, and we just ask that if you are feeling sick or whatnot, please refrain from looking through the eyepiece. The sanitation required between each person would actually destroy the optics, we have figured out, and therefore we can't really sanitize the eyepiece as well as we would need or want, and we don't want to give other people really any nasty bugs. There's a whole plethora of them, including the current plague, and we'd like to avoid that. Right, so it looks like some of you have run away. Were there any last minute questions? Nothing.
So go do some observing. You got a great night.
So have a great night. Thank you for coming out. And thank you for everyone who joined us online.
Bye.